Now we're ready to solve our first real Schrödinger equation, and we're going to do it for the simplest case of a constant potential which we'll set equal to V. So with this simplification, we can now remove the middle term in our Schrödinger equation and just call this constant term here E minus V. We're going to bring all the other constants over as well, the 2m and h bar squared, resulting in this equation here, which says that the second derivative of the spatial part of the Schrödinger equation is just equal to this constant times the solution of the Schrödinger equation. Equations of this sort are solved by exponentials. Remember that we're solving for the spatial part. The full wave function, of course, is the product of this spatial part with the time part that we found in general for all time-independent Schrödinger equations to be equal to e to the minus I e over h bar t. So remember that any spatial solution we find in everything that follows will be oscillating up and down in time with an angular frequency given by e over h bar. So, as long as we remember that, we can go ahead and solve for the spatial part. So returning then to this trial exponential solution, the first derivative is just ik a e to the I kx, and the second spatial derivative is just minus k squared a e to the I kx, which is just equal to minus k squared psi. So indeed this does solve the Schrödinger equation, providing that minus k squared here is equal to 2m e minus v over h bar squared. There's a minus on this side of the equation, so actually this whole thing then is just equal to k squared. Now this has an interesting consequence. We can set the potential equal to 0 if it's a constant everywhere. We don't have to worry about changes. So in zero potential then, we know that the energy of the particle must just be its kinetic energy. And this is equal to, well, let's put the v equal to 0 here. So 2m e over h bar squared equals k squared. So E is equal to h bar squared k squared over 2m. This is a very interesting result. If we set the momentum of the particle to be equal to h bar times the wave number of the particle, then we see that this expression for the kinetic energy reduces to p squared over 2m. But this is just the classical result, and indeed the quantum mechanical expression for momentum is just h bar k. So we see that in a constant potential, the wave function is just a plane wave, written out in the slide here, including the time-dependent part, that the kinetic energy is given by p squared over 2m, the classical result, so long as p is h bar k. We're going to move on to consider the solution of the Schrödinger equation in a variable potential. So before we do that, let's look at some constraints on the wave function, some boundary conditions that apply because of the form of the Schrödinger equation. On the left of the Schrödinger equation, one has the second derivative. And on the right of the Schrödinger equation, the energy. So this tells you that if the energy of the system is to remain finite, the second derivative must remain finite. So a requirement for the physical solution of the Schrödinger equation is that the second derivative of the wave function be finite. If the second derivative is finite, this requires that the first derivative must be continuous. For this to be the case, the wave function itself must be continuous. So, when we look at problems in which the potential is changing, we are going to use these two boundary conditions, that the wave function and its derivative across some change in potential must be continuous, i.e. we set the wave function just one side of the barrier equal to its value on the other, and the same for the derivative. The second derivative can, of course, and does change.